Hi everyone, this is Carolyn Schechter, and today I'll be talking a little bit about hemoglobin, how it binds oxygen, and how it perfuses that oxygen throughout the body. So hemoglobin is a protein found in red blood cells that transports oxygen from the lungs to tissues of the body. It's made up of 4 chains, 2 alpha subunits and 2 beta subunits, and these subunits form 2 alpha-beta dimers. And each subunit contains a heme group. The heme group is what actually transports oxygen, and these heme groups contain a central iron atom, usually in the 2+ ion state. Almost always in the 2+ ion state, because the 3+ ion state cannot bind oxygen. Hemoglobin has 2 states, the T state and the R state, and as we learned, T state has lower oxygen affinity than R state. So when it is unbounded to oxygen, it's in the T state, and when it binds, it becomes the R state. Now I'm going to zoom in just a little bit into this picture, and as we can see, we have our heme group in here, and the red inside of there, that's the iron atom inside the center of that heme group. So moving on. Oxygen binds to heme groups in hemoglobin, as I mentioned before. The organic component of these heme groups is called protoporphyrin. Fe2+ sits at the center of this organic component and is about 4 angstroms outside the plane when it is not bounded to oxygen. It can form 2 additional bonds called the 5th and 6th coordination sites. The 5th coordination site is occupied by a histidine residue, and the 6th is available for oxygen binding. So in this photo here, we can see the histidine residue. And on top of it, this is a bound heme group with oxygen on top. And here's just a picture of the molecule in its structural form. So binding of oxygen at the 6th coordination site rearranges the electrons in iron, and it makes the iron molecule smaller so it can fit into the plane of porphyrin. As we can see here, the iron molecule here is larger, and once it binds to oxygen, oxygen rearranges its electrons, makes it smaller, and it is now within the plane of the organic component. The bound oxygen also forms an H bond with distal histidine. Distal histidine is just something that prevents the iron from becoming a 3+ ion, because that 3+ ion cannot bind oxygen. And now when it is bound to oxygen, it helps stabilize that oxygen on the heme group. The histidine at the 5th residue will move with this iron atom since it's directly attached to the iron atom, which leads us to some more structural changes within hemoglobin. The histidine residue is a part of one of the alpha subunits of hemoglobin. So that alpha subunit is also going to move when iron is pulled into the plane. The carbonyl terminal end of this alpha subunit lies between 2 of the alpha-beta dimers. So the structural change at iron is transmitted to the other subunits and results in the change from the T state to the R state across the hemoglobin molecule, which now has the higher oxygen affinity and now will bind at all 4 heme groups. The AB subunits will then rotate 15 degrees with respect to each other. So based on this picture here, we can see they're rotating about 15 degrees. It almost looks like they're coming closer together right in here. So this is oxyhemoglobin and this is deoxyhemoglobin. So as we keep going, so now we're going to talk a little bit about the binding capacity. Oxygen binding capacity is mostly affected by 2 factors: the partial pressure of oxygen in whatever environment we're talking about, and the pH of the blood in whichever environment we're talking about. So when we're talking about partial pressure, the partial pressure of oxygen in the lungs is about 100 torr, while the partial pressure of oxygen in the bloodstream and tissues drops to about 20 torr, depending on how far away we are from the lungs. So this partial pressure decrease, it increases the amount of oxygen released from the hemoglobin. So it decreases the affinity of the hemoglobin oxygen complex. So the oxygen will be released from the hemoglobin and it'll move back into that T state. And it releases about 66% of its oxygen, as we can see on this graph here. This is 20 torr here. And then at about where we are at the lungs, we got 66% of our oxygen dropping. In the lungs, it's almost 100% bound. We also have to take into consideration the pH of the blood in the lungs versus the pH of blood in the tissues. So CO2 and hydrogen ions are heterotropic effectors that enhance oxygen release in something called the Bohr Effect. H ions protonate histidine residues in hemoglobin, which then forms salt bridges with aspartate, stabilizing the deoxygenated form of hemoglobin, which thereby release more oxygen. So the more acidic we are, the more deoxygenated hemoglobin we're going to have. The pH in the lungs is about 7.4, and the pH in tissues is about 7.2. So the tissues here, as you can see, are more acidic, and therefore are going to have more H ions to protonate histidine and form those salt bridges. And it enhances oxygen release within the tissues, which is what we want. CO2 also stabilizes deoxyhemoglobin by reacting with the terminal amino groups to form the negatively charged carbonate groups. That just means that we're stabilizing the T state even more. So it moves it from 66%, so as we can see here with CO2, to about 88%. If we didn't have any CO2, we'd be about 77%, which is still more than that 66% we would have with just a partial pressure change. CO2 in tissues also makes the environment more acidic because it reacts with water via the enzyme carbonic anhydride. This reaction yields bicarbonate. Bicarbonate is right here, and which decreases the pH in tissues because it also releases, I'm sorry, I underlined the wrong thing there. Bicarbonate is here, and it releases also H plus ions. I apologize for that. Erase that right here. So we have our bicarbonate and our H plus ions, which decreases the pH within the tissues. Bicarbonate is carried throughout the bloodstream to the lungs. It's converted back into CO2 and then exhaled. That's actually how most of the CO2 leaves our body. Some CO2 leaves our body when it attaches directly to hemoglobin, but that's a pretty low number. Most of the CO2 leaving our body leaves as bicarbonate. So that's pretty much all I have for you guys. If anybody has any questions, or if you disagree with me on anything or think I missed anything, please let me know. And I have my references here. I mostly used our biochemistry book, but I have a few websites that I think were very helpful. So thanks for listening.